Solving a three-variable, three-equation system necessitates that we reduce the system down to two variables and two equations. We have the liberty to choose whichever variable we would like to eliminate, but for the purposes of this exercise, we're going to focus on the letter Z. In order to eliminate the letter or the variable Z from two of the equations and create two new equations, we're going to pair off the equations. So I'm going to create two pairs. We're going to first look at this pair, and then we're going to look at this pair. Don't be alarmed by the fact that equation 2, the second equation in the list, is going to be used twice. That is allowed under the solving of three variables systems. Looking at the first set, we see 5x minus 2y minus 4z is equal to 3, and 3x plus 3y plus 2z is equal to negative 3. If I want to eliminate the variable z, I can multiply the second equation by 2 and get opposite coefficients in front of the variable z. So that's what we're going to do. We're going to multiply this second equation by 2 and get 6x plus 6y plus 4z is equal to negative 6. Now, I don't need this version of the second equation anymore. Adding down, I have 5x and 6x is 11x. Negative 2 plus 6 is positive 4. The z's have opposite coefficients, so they will add to 0. And 3 plus negative 6 is negative 3. This, as a combination of those two equations through allowed operations, is the first equation for my system, my new two-variable system. Now we take the other pair and look at the second equation, 3x plus 3y plus 2z is equal to negative 3, and the third equation, negative 2x plus 5y plus 3z is equal to 3. I still want to eliminate the variable z. If I switched over to x or y, that's not going to help me when it comes time to create my new two-variable, two-equation system. So we need to stick with z. Unfortunately, in order to eliminate z from this pair of equations, I'm going to need to multiply both of them. So in order to do that, I'm going to multiply the top equation by negative 3 and get negative 9x minus 9y minus 6z is equal to 9. And I'm going to multiply the bottom one by 2. And after we multiply the bottom one by 2, you can see that we get opposite coefficients in front of the variable for z. I don't need either of these two anymore. I have these two new versions to use. I'm going to add down and end up with negative 13x plus y is equal to 15. This will be the second equation from my two-variable, two-equation system. Once we're onto those two equations, solving them just goes back to the way that we solved any system previously. Because I already have them lined up in standard form, I'm going to eliminate the variable y by multiplying the bottom equation by negative 4. That's going to change this equation to 52x minus 4y equals negative 60. Adding down, I'm going to get 11 and 52 is 63. The y's will add to 0, eliminating the y variable from this two-variable system. And then negative 3 plus negative 60 is negative 63, which is certainly convenient as it leaves me with x is equal to negative 1. Now that I know that x is equal to negative 1, I can work backwards through any of the equations that I have in order to determine the other variables. It makes the most sense to take this x back into one of these two equations, as they only have the y in it that I can figure out next, and I'm not going back all the way to the one with three variables, as that'll just get confusing because I won't know y or z. So taking x back into either one of those equations, for the purposes of this exercise, we'll choose the second one. But for negative 13 times negative 1 plus y is equal to 15. Negative 13 and negative 1 is 13, plus y is 15, so y would be 2. I now have two parts of my solution. Because we're in three variables, my solution will take the form of what's called an ordered triple, which is a sequence of coordinates written in the order of x, y, z. I have two of them. I've got the x and the y. In order to bring the z back in, I am going to have to go back to the original equations. And so for the purposes of this question, I'm going to choose the middle equation. It looks like it has the most positivity over on the left side of the equation. This would probably be the easiest one to sub into. So I'm going to choose that equation, and I'm going to use my known x's and y's in order to substitute and find what z is. So that equation was originally 3x plus 3y plus 2z is equal to negative 3. Subbing x is equal to negative 1 and y is equal to 2 plus the 2z is equal to negative 3. 3 times negative 1 is negative 3. 3 times 2 is 6. This is 2z. That's negative 3. This makes a 3 here. Now we're down to just a one variable, very simple two-step equation. And we end with z is equal to negative 3. So the last part of the ordered triple would be negative 3. So our final solution, and if you want to call it the solution set, you can use our braces to indicate that it is a solution set, but you don't have to. You can simply write just the ordered triple negative 1, 2, 2, negative 3. But certainly you still have the option, if you'd like, to check all of those solutions. So we had an ordered triple of negative 1, 2, negative 3. And we could sub those three numbers into any or all of these equations. Now, I don't need to do the second one because I already know that that one works. That's where I got it from. So that's just going to be confirmation bias if it ends up being right. I really would want to try it in the other two to ensure that it is correct. So 5 times negative 1 minus 2 times 2 minus 4 times negative 3. And the hope is that that equals 3. Well, this is negative 5. That's negative 4. That's plus 12. And it does equal 3. And then you can check the last one. Negative 2 times negative 1 plus 5 times 2 plus 3 times negative 3. 2 plus 10 plus negative 9. Does that equal 3? And it certainly does. So we're not unnerved by the fact that 3's and negative 3's keep showing up over here. We saw that we had two different routes to create a 3 based on the coefficients of the the three variables. But we checked our solutions. We know they work in the middle one because that's the one we solved it in. And then we check it in the other two to make sure those work as well. There was a lot happening in this procedure. So let's go back over it one more time just to make sure we recognize all of the steps. So we start by choosing two pairs of equations. I chose the first two and then the last two as the two pairs. And then from those two pairs, we eliminated the variable z. In the first pair, I only had to multiply the bottom equation in order to adjust the coefficients. In the second pair, I had to multiply both equations in order to adjust the coefficients and get rid of the z. After I added those two pairs of equations together, I got this new system down here. Solving that two variable system got me both x and y. That was 2/3 of the ordered triple. I take those two numbers back into any one of these equations. I chose the middle one because of the positives over here. Subbing those in, negative 1, 2, getting that z was equal to negative 3, and then back substituting all three parts of the ordered triple into the other two equations to confirm that they work. Should you find yourself in a time bind, obviously this is the step that you would skip. You would hope that your solving was sound in all of the other steps and you wouldn't have to go back and back substitute all three of them into two more equations. But if you have the time, this is an ideal option because there is a lot of opportunity for a sign to be messed up, something to go wrong somewhere little, even in just adding these, or adding the coefficients of the y's, or adding the constants that are on the right side. There's just too many little things that can go wrong, where early on, at the very least, you want to practice good habits, and back substituting certainly falls into that category.